Hi everyone. So we're going to finish off our unit today on derivatives of logs and exponents. And I'm starting off on the page that we started with because what we're going to do today is something called logarithmic differentiation. And essentially we're going to use logarithms to differentiate functions that would ordinarily be quite difficult to differentiate. And what we're going to utilize to do so is all of our log laws. So I wanted to bring those to your attention again because we started with those so that you are familiar with them because we're going to use those all the time today. Okay, so we have the product law. When we add two logarithms with the same base, we can multiply the two arguments together, or we can also split up. If we have two things that are being multiplied together and we take the log of those, we can split that up into two separate logarithms. Okay. Also, if we divide one thing by another and take the log of that, we can split that up into the difference of two logarithms. And then finally, there's the power rule, where if we take a logarithm and then raise it to an exponent, that's equal to that exponent times the logarithm. Okay, so I did want to remind you of these three laws in particular because we are going to be using those a lot today in the work that we're going to be doing. All right, so let's move ahead a little bit to 8.6, and we're going to move to logarithmic differentiation. So essentially what we're going to do is look at a function like this one that is pretty nasty. If we wanted to differentiate this without logarithms, we would have to, if you think about it, deal with quotient rule. We'd have to deal with, in the numerator, a product rule. We'd have chain rule in there in both the numerator and denominator. It would not be very fun. It would be really, really complex. And so what we can do instead is we can take the ln of both sides. And then try and break apart some of the right side of the function with all the x stuff in it a little bit to make something that's a little bit easier to differentiate. And we will have to do some implicit differentiation here because instead of having y equals, we're going to have ln y equals. But we've dealt with that before and we can deal with it again. Okay, so what we're going to do first is start by taking the ln of both sides. So we're going to have ln y equals ln of x to the 3/4 times the square root of x squared plus 1 over 3x plus 5 to the 5. Okay, so I've just taken the ln of both sides. But now what I can do with the right side is I can break this up into several logarithms using the product and the quotient rules, right? So on the left side, I still have the ln of y. But on the right side, I'm going to have the ln of x to the 3/4 plus the ln of, and maybe I'll switch this into now a fractional exponent, x squared plus 1 to the 1/2 instead of the radical, and then minus the ln of 3x plus 5 to the 5. Okay, and now I'm going to go even a step further and use my power rule to bring all of these powers in front of the logarithms. So I'll have ln y, equals 3/4 times ln x plus 1/2 times the ln of x squared plus 1 minus 5 times the ln of 3x plus 5. Okay, now this is quite nice because remember if y equals ln x, the derivative is 1 over x. So these derivatives are quite nice to deal with. On the left side, if I'm taking the derivative of ln y, I'm going to basically have 1 over y times dy dx. And that's going to equal 3/4 times 1 over x plus 1/2 times 1 over x squared plus 1. And then we have to multiply that by the derivative of x squared plus 1, which is 2x, minus 5 times 1 over 3x plus 5 times the derivative of 3x plus 5, which is 3. Okay, if we simplify this a little bit, we're going to have 1 over y times dy dx equals 3 over 4x, and then here the 2's cancel. So plus 1 over x squared plus 1, and then minus 15 over 3x plus 5. Okay, now to isolate dy dx, we just need to multiply both sides by y. So if I multiply both sides by y, I'm going to get dy dx equals y times 3 over 4x plus 1 over x squared plus 1 minus 15 over 3x plus 5. Okay, now I didn't really want my derivative to be in terms of y. I wanted to be in terms of x, but I know what the original function was. The original function was y equals all this stuff. So I can take all this stuff and now sub it in for y over here. So my final derivative will be, what was y? X to the 3/4 times the square root of x squared plus 1 over 3x plus 5 to the 5 times this, which is 3 over 4x plus 1 over x squared plus 1 minus 15 over 3x plus 5. And that is a lot easier to do than if we had tried to differentiate without using logarithms. Okay, so let's try another one. Differentiate y equals x to the power e to the x. Okay, so we're going to take the ln of both sides again, and we're going to have ln y equals the ln of x to the power e to the x. And now, of course, what I can do is I can bring this e to the x out in front of the logarithm on the right-hand side. So I'm going to have ln y, ln y, there we go, equals e to the x times ln x. Okay, and now on the right side, I just have to deal with a product rule. So now I'm ready to differentiate with respect to x. Okay, so on the left-hand side, I'm going to have again 1 over y times dy dx. And on the right side, I have u prime v. Well, u prime and u are the same. They're both e to the x. So u prime is just e to the x. V is ln x plus uv prime. U is e to the x. V prime is, if v is ln x, v prime is 1 over x. Okay, then again, to isolate dy dx, we need to multiply both sides by y. So dy dx is going to be y times e to the x ln x plus e to the x over x. And then I can do the exact same trick I did before, where I take what y was originally equal to and sub it in here. And so I'll get that dy dx equals x to the power e to the x times e to the x ln x plus e to the x over x. And that's my derivative. Okay. All right, so we're going to try one more and then we'll be done. Okay, differentiate. Y equals the square root of x times x squared plus 1 to the 10. Okay, so let's take the ln of both sides. Okay, and then again on the right, I'm going to break this down into the sum of two logarithms. So ln y equals the ln of, instead of square root of x, I'll write it as x to the 1/2, and then plus ln of x squared plus 1 to the 10. And then just like the first question that we did, I'm going to bring the powers in front of the logarithms, or the exponents rather, I should say. Oh, I can't. Why do I keep doing that? Ln. I forget about the L, or the N rather. Ln y equals 1/2 ln x plus 10 ln x squared plus 1. Okay, and now I will differentiate both sides with respect to x. So on the left, this is going to be a bit of a refrain. We're going to have 1 over y dy dx. And on the right, I'm going to have 1/2 times 1 over x plus 10 times 1 over x squared plus 1 times the derivative of x squared plus 1, which is 2x. And now I'm going to simplify the right a little bit. So on the right, let's see, I have 1 over 2x plus 10 times 2x is 20x over x squared plus 1. And I'm going to keep going here. I'm going to write this as with a common denominator. So that common denominator would be 2x times x squared plus 1. And then from the first term, I need to multiply by x squared plus 1 over x squared plus 1. So this is going to be x squared plus 1. And then from the second term, I need to multiply the second rational expression by 2x over 2x. So this is going to be 20x times 2x. Okay, and then all together, that's going to give me, let's see, x squared plus 20x times 2x is 40x squared. So that's 41x squared plus 1 over 2x times x squared plus 1. And all of this is equal to 1 over y times dy dx. Because I haven't done anything to the left side. I've just sort of simplified the right side. Okay, now I'm going to multiply both sides by y. So I'll have dy dx equals y times 41x squared plus 1 over 2x times x squared plus 1. And then I'll take whatever y was equal to, which is this, the square root of x times x squared plus 1 to the 10. And I'm going to sub it in for y over here. Okay, so if I continue, dy dx equals the square root of x times x squared plus 1 to the 10 times 41x squared plus 1 over 2x times x squared plus 1. Okay, and now we actually have a common factor in the numerator and denominator because there's a common factor of x squared plus 1. So we can cancel that. So this will cancel with one of these. And all together, dy dx will be the square root of x times x squared plus 1 to the 9 times 41x squared plus 1 over 2x. And that's about as far as we'll go. And that will be it for today. And I'll see you guys again.